Hello everyone, in this video we are going to discuss and explain the proportional controller. First, I want to say that the most common controller in the control system is the PID controller. The PID consists of three controllers: the proportional controller, the integral controller, and the derivative controller. Each one of these controllers has advantages and disadvantages. So we are going to discuss each one of them in detail. And in today's video, we are going to start with the proportional controller. But first, I want to remind you with an important note here. If we have this block, which may be this one or this one, and we have here an input to this block and output from this block. Let's say that this is y and this is x, and we have here, for example, 5. It is a multiplication process. So in that case, the output, which is y in this case, will be equal to 5 multiplied by x. So what I want to say here that the output from any block is equal to the input multiplied by what is inside the block. Okay, now let's go to the proportional controller. The proportional controller is very simple because it only multiplies the error signal by a value called Kp, and the output from the controller here will be the input to the process. So the main job of the control system engineer here is to choose the proper value for the Kp of the controller that can minimize the error signal as much as possible and achieve the desired output from the system. And today I will show you how you can get a certain value on the output by changing the value of the Kp. But before explaining this, I want to show you the hardware implementation of the proportional controller. Here is the circuit that we use as proportional controller. You can put here the input. We can put here the input, and here is the output, and the relation will be V output over the input will be equal to Kp, where Kp equal to R2 over R1. So if we want to change the value of Kp, we can change the resistor values here. But in our course, we are not gonna implement this because we are gonna use the Arduino instead, because we can do this in programming, or we can do this by implementing a hardware circuit like this. So if we want to put this circuit in the system here, the input here will be the error signal E of S, and the output here is the U of S value. Also, I want to mention that here there is no block for the feedback here, and this is only for simplicity. Also, I want to mention that maybe there is a minus sign here, but I neglect this because it is not important in our course. Okay, so now let's go to the next step. Okay, now we want to study the steady state error of a system that has a proportional controller. So let's start with a first order system. But the question here is, what is the first order system in real life? I can give you a simple example here. The first simple example here is the RC circuit, the circuit that has a resistor and a capacitor. And I will explain this in detail in the next video, so don't worry about that. Maybe if you search it on Google, you will find some other first order systems in hardware. It is very good to understand how these equations, how this equation or similar equations are represented in hardware. Okay, here a note that I want to say. This is the first and last video that we are gonna explain an equations, because our aim, our purpose of this course is to focus on the hardware, because there are a lot of materials and tutorials that explain the theory and the equations and all of this stuff. So I will explain this just for clarification, but in the next videos you have to know the equations and make the theory comparisons yourself. Okay, so anyone studied the control system classes will know that the output over the input is called the transfer function, or the closed loop transfer function, and it is equal to the open loop transfer function over 1 plus the open loop transfer function. So we can say it is equal to Kp multiplied by 1 over tau s plus 1, like this one here, over 1 plus the open loop here again. And you can simplify this equation here to become like this. Okay, let's now calculate the error. We can calculate the error from here. It will be equal to the R of S, which is the input, minus the output or the measured value. So E of s equal to R of s minus Y of s, and this will be equal to R of s minus Y of s, and Y of s we can get it from here. We can put this here, and R of s will be multiplied in this part. So we have here R of s, and this is the value of the error. If we want to calculate the steady state error, and the steady state means when the system reaches the steady state, so we can say that the steady state error is equal to limit s goes to 0, s multiplied by the error of s. So we can replace the input here by 1 over s because we are using a unit step input, and in that case the error will be equal to 1 over 1 plus kp. And remember, the error is equal to the input in the steady state minus the output in the steady state. And we can now ask an important question: what is the best value for the error? The best value happens when the input in the steady state is equal to the output at the steady state, and in that case the error will be 0. And when the error is 0, this means that we reached the desired value. Okay, now let's take an example here with values, and after that we are going to explain the same example in the MATLAB program using Simulink. So we have here the steady state error is equal to 1 over 1 plus kp. So what we need to do to make the error become smaller, we need to increase the kp because it is in the denominator. So if we increase the kp, the steady state error will decrease. Okay, so to understand this, we need to take an example with the values. So let's start by assuming that the input is unit step input, and unit step means that the input is equal to 1. And unit step in hardware means it is just a simple thing. We can say that we need a battery that provides 1 volt. This is a unit step, so it is not something difficult. And let's assume also that the kp is equal to 1. In that case, we can calculate the steady state error from this equation. It will be equal to 1 over 1 plus 1, so the result will be half. So now, how we can calculate the output here? We know that the steady state error is equal to the input at the steady state minus the output at the steady state. This is half, this is 1 from here and here, and we can say that the output at the steady state will be equal to half. Okay, that is great. Okay, now I want to ask you a very important question here. Is there any problem with these numbers here, the value of the input and the value of the output? I can say yes. These numbers indicate that this system is not efficient because the output CSS is equal to half, and the reference input is equal to 1. And don't forget that I explained the reference meaning in the previous videos. We said that the reference input is the desired value from the system, and desired value mean that this is the value that we need the system to provide. So the system provide now half, but we want it to be 1. So the efficiency of this system is equal to 50%. This is not good. But the question now is how we can improve the efficiency of the system, how we can make the output of the system closer to the input value or closer to the reference value. We can do this by increasing the value of the kp. So let's assume that the value of kp is equal to 3. And how we can do that in the hardware? Again, we can do that if we are implementing the proportional controller in software, for example, inside the code of the Arduino, then we need to change the value in the code. It is very simple. But if we are working on hardware like this circuit here, we can just change the values of these two resistors to make the kp equal to 3. For example, we can choose this to be 3 and this is 1 ohm, and we obtain the kp equal to 3. So it is very simple to implement this. Okay, so in that case the steady state error will be 1 over 1 plus 3, and the result is 0.25. In that case the output will be the steady state error will be 1 minus CSS. So we can say that the CSS is equal to 1 minus ESS. It will be equal to 1 minus 0.25. This will give us 0.75. So the value was half, and now it is equal to 0.75. So increasing the value of the KP increases the output and decreases the steady state error. But I want to mention here a very important note about the proportional controller. In real hardware, we can't increase the value of KP to infinity. We are limited by the physical boundaries or the physical specifications of the hardware, for example, the operation amplifier. So we can't increase it to infinity. And this means that we can't make the error is equal to 0. We can't make it equal to 0. So finally, we can say that increasing the value of KP will decrease the steady state error, but will not eliminate its value. And this is why we need to add another controller like the integral controller. Okay, now let us discuss an important topic here that I told you we are gonna explain. Let's assume that we need to control the behavior of our system. What does this mean? This means that we want to get a specific output. For example, we need the system to provide a value equal to half. How we can do that? As a control system engineer, how we can make the system provide us with any value we need? In this case, we need the value to be equal to half. And the answer to this is very simple. You can do this by changing the value of the KP. So how we can do that in steps? First, you need to determine your input, and we assume that the input is equal to 1. It is a unit step. Okay, what is your desired output? The output that we need is equal to half. Okay, we can say that in that case, the steady state error will equal to 1 minus half, and this is equal to half. Okay, so we need the steady state error to be equal to half. How we can do that? It is very easy. You can put the equation here. So from this, you can calculate the required value of the KP. And if you are using the Arduino, you can change the value of the KP inside the code. Or if you are using this hardware implementation, you can change the values of the resistors to achieve the required KP. Finally, I hope that you understood the proportional controller well. I supposed to explain this example using the simulation, using the MATLAB program, but because the video become now longer, I will explain this in the next video.